Hello, my name is Nigel Glover. I work for Brooks Instrument out of our Atlanta, Georgia office, and I'm going to talk about variable area flow meters today. As you know, there are a lot of different ways to measure flow in a pipe. You can use mag meters or Coriolis meters, thermal, ultrasonic, vortex, positive displacement meters. Um, so a lot of different ways to measure flow in a pipe, and all of those flow technologies exist for various reasons. Some are very accurate, some can handle slurries and solids and things. And we're going to talk about variable area flow meters or rotometers, and in particular the Brooks rotometers. This is a Brooks show rate. A lot of people have these in their plants. Fluid goes in through the bottom, out through the top. There's a valve here. You open the valve, the float goes up, and it indicates flow. It's a very simple way to indicate flow. Why would somebody use this type of flow meter as opposed to a Coriolis meter or a mag meter or a vortex meter or something like that? Well, one reason would be this is cost effective. This is also a very repeatable way to measure flow, and we'll show you some slides here in just a minute on what I'm talking about. This is very easy to install and maintain, very easy to own. Wide variety of materials. The bottom block and top block can be made of brass or stainless or kynar. No power required, see, no wires, low pressure drop. It's a very easy meter for a guy in a plant to put in so he can see the flow. Let's see what happens on the next slide. How does a rotometer work? Well, there's a tapered tube in here, okay? The tube is tapered, and there's a float that goes up and down as the fluid goes in through the bottom and out through the top. And the float rises, and the space between the float and the tapered tube, or the wall, that's the part that varies, and that's why we call it a variable area flow meter, okay? What happens is, you can see from here the float has a set of forces pushing the float up and a set of forces pushing the float down. The upward forces are the viscosity or the thickness of the liquid, and the flow rate lifts the float, and the density of the gas lifts the float. The downward force, let's see, the taper of the tube, if I make the taper of the tube larger, the float falls lower. So if I make the taper a higher angle, the float sinks. If I make the float out of a different weight, if I make it heavier or lighter, if I make it heavier, it's gonna sink. And in a gas system, the back pressure pushing down on the system is a downward force. Well, what happens is we want the upward forces to equal the downward forces, and then the float sits still. And that's what we want in a rotometer. And that's called a dynamic balance. And it's where the upward forces equal the downward forces and the float comes to rest, okay? There's 5 basic parts of a variable area flow meter. There's the tube, and the tube is made of glass in this one, but it can also be made of metal or plastic. I'll show you some of those in just a minute. There's a float that goes up and down inside here. You might not be able to see it, but there is a little spherical float, and when we get to some of the bigger meters, we'll see different shaped floats that aren't spheres. There's a scale that may be on the glass tube, or it may be a detached scale, looks like a ruler attached to the side of the body. There's a body or a housing, and then there's some end fittings. And I separate the body and the housing from the end fittings because you don't get to choose what the body's made of, but you do get to choose the materials for the end fittings or the connections, okay? Now, why would somebody want to use a glass tube meter? They can see the flow. Let me show you a larger glass tube meter, okay? This one is the Brooks GT1000. It's a larger glass tube meter. Flow goes in through the bottom. There's a dust cap here. This is a threaded connection, can be a flanged connection with bolt holes in it. In through the bottom, out through the top, and the float in here goes up and down. Okay, there's a float that goes up and down, and then there's a scale on the outside showing you, gallons per minute of water. That's what this one is. Okay, and this one can be, instead of in through the bottom, it can be in through the back and out through the back. Okay, but the flow is always going to be going up. So this is a glass tube, and people are going to use glass tubes because you can see the flow. Why aren't you going to use a glass tube? Well, you've got some temperature problems to be concerned with. 250 degrees F, that's pretty hot to be in a glass tube. I think most plants are going to cut that off closer to 100 degrees F. Any fluid that is warmed up, maybe glass isn't the best way of doing it. You don't want high pressures in a glass tube meter just in case. Okay, a lot of these meters get rated for pretty high pressures. This one's rated for 200 psi. I don't believe I'd want to put 200 psi in a little glass meter. We might want to go to a metal tube meter if the pressure gets up too high. No steam, that you'd be changing the temperature of the glass too fast, it might break. It is borosilicate glass. It is very, very strong, very rigid. It's similar to your Pyrex mixing or measuring cups you may have in the kitchen. We don't want any caustic. Why don't you want caustic in glass? It etches the glass. It causes the glass to frost on the inside, and you won't be able to see the float. Okay, so glass tubes are great because you can see the flow, you can see what's going on. As you open the valve, you see the ball go up, and you feel comfortable that there is flow going through the system. But for safety reasons, we do want to limit glass when there's temperature and pressure concerns. So what do? We go to a metal tube meter. Well, on this little one, we have a metal tube meter. This guy is called the Brooks 3750. And there is a metal tube right here, and it has the same takeout dimensions, in through the bottom, out through the top, and the same valve combinations are available on it, and roughly the same flows for the glass tube show rate and the metal tube Armite. So similar flows, but this one has a metal tube. Much higher temperatures, much higher pressures are available through this one. This one says 1600 psi and 400 degrees F. Okay, now you can put some good process fluids through here. Big disadvantage of this is you can't see the float. Okay, as you open the valve, the float may be going up and down, but you can't see it. The float inside here is a little torpedo that has a magnet in it, and the magnet is coupled to an indicator on the outside. So as it goes up and down, maybe you can see the indicator needle is going up and down there. So as the float goes up and down inside the metal tube, there is a pointer here that goes up and down that follows it. So it has a magnetic linkage in here. There's a jeweled bearing here and a counterweight and two follower magnets to follow the actual float magnet that's going up and down. So it's a very sensitive indicating needle, but it's close coupled to the float, and it works extremely well. Now once we've got a magnet going up and down, we can also, out here on this side, we can put some switches, or we can put a 4 to 20 milliamp transmitter and send a signal back to the control room. So this one becomes a platform we can build on and get some additional information out of it. Historically, customers would put a low flow switch to alarm that there's no flow if this was, say, on a sample line, or a cooling going to a bearing or something, or to a pump seal. You'd want a low flow alarm to tell you that there's no flow. Well, we developed a solid state transmitter, a 4 to 20 milliamp transmitter that will go on here, and it senses the position of the magnet. You know how a magnet has a north pole and a south pole and an equator. There are flux lines coming from the magnet. We have a solid state sensor that mounts right up next to the tube, and it can detect if the magnet is down here or in the middle of the flow path or up at the top. It can detect where the float is based on the angle of the flux lines. So it's a little solid state sensor, and then we can convert that to a 4 to 20 milliamp output. Works great. It's a very rugged, it's just a simple 2-wire transmitter, and no heart, no smart, nothing, just 2-wire transmitter. And but that's a lot more information to get back to the control room. Say this is a sample line, and you get the sample flow set up to where you want it. You go back to the control room, and you tell the guys in the control room that this is normal flow, and if the flow starts dropping from there, maybe you need to go change the filter. And if the flow drops all the way to 0, maybe you need to get up now and go do something. But if the flow is just simply dropping a little bit each day, you can predict when you would need to go change the filter or do something to the sample system. So having a 4 to 20 milliamp output signal is sometimes better than just having a yes and no contact switch on a metal tube meter. Why else do we want metal tube meters? Well, lots of reasons. On the larger ones, ½ inch, 1 inch, 1.5 inch, they are similarly priced to the glass meters. This one's not similarly priced, so that bullet item does not match. This guy is much more economical than this guy, factor of about 2.5 times as expensive, maybe even 3 times as expensive. But if you break this once, you've shut your process down, and you've certainly paid for this. So, and you're not going to break this. This is very rugged, very rigid. You're not going to break it. But the forklift truck driver may run into the pipes and break something, so it might break. So for safety reasons, maybe a metal tube meter is a better way to go. The downside is you can't see the float. Okay. Now, while we're talking about glass tubes and metal tubes, I did show you the larger flows in the glass tube, the GT1000. This can be NPT threads or flanges for the inlet and the outlet. We can put valves on it, or we can close couple a needle valve to it. But for safety reasons, if you don't want glass, now this one's very safe. It has an acrylic shield around it. There is a heavier duty version of this that has packing glands at the top and the bottom instead of just a simple O-ring seal at the top and the bottom. And it has structural side plates instead of a cast aluminum frame. So this is the GT1000. There is a beefier one called the 1100 series that's much more substantial. Uses the same tubes and floats, so the same flows, same sizing program. But it's a much more substantial, rugged meter. Plant guys like it a lot because they can take the tube and float out, clean it, put it back in, has packing glands and very sound, solid. This one can also be taken apart and cleaned very easily. It has an O-ring seal at the top and the bottom. But for safety reasons, somewhere around 100, 150 psi, 100, 150 degrees F, somewhere in there, you're going to want to stay away from glass and migrate towards metal. So we have some metal tube meters that'll do these same flows, 3809 and 3810. I only carry around a nice lightweight 3810. Has threaded connections. There are flanged connections available. There's a float inside here that goes up and down, and it's connected to the needle. And as I push my finger up through here and raise and lower the float, you can see that the indicating needle is coupled to the float. So the float goes up and down, has a magnet in it, and out here on this spindle is a follower magnet that goes up and down and drives the needle. We can put the solid state transmitter in here, that same technology that measures the angle of the flux lines, can go right behind the dial on a circuit board. Back here we can put the little solid state sensor and its amplifiers and everything to get it to a milliamp. And on the 3809, 3810 series, it's a Hart Smart transmitter. It's got totalizers, and we put a lot more things into it rather than just a simple 2-wire transmitter. So you can get a lot more information out of it. So this can be a very economical way to measure flow in a pipe, or we can add the transmitter to it and make it a very versatile as well as a fairly economical way. It will compete with vortex meters and orifice plates with differential pressure gauges and things. It's a very good meter for all those reasons. Okay, so that's the metal tube meter. Now, I did mention that we can make plastic meters. Wonder if that slide comes up. No, it doesn't. But we do have a line of acrylic-bodied meters. These are plastic-bodied acrylic meters. We bought a company called Key Instruments. They are leaders in the world in machining acrylic. There's a tapered tube machined in here. The scale is printed on the front of the meter. Open the valve, the ball goes up. These are typically for air and water only, very simple applications. If it gets to be anything more than that, let's move to a Brooks show rate or something more substantial than that, like the larger metal tube and glass tube meters. For accuracies, this one's not the most accurate meter in the world, plus or minus 10% of full scale. We can make a taller version of this. This is the 1350. The taller one is the 1355. Gets better accuracy simply because it's taller. It's a plus or minus 5%. And then the larger glass tube meters are standard at plus and minus 2%. And for an additional fee, we can make it a 1% device, do a multiple point calibration. Okay, so tubes are almost always cone shaped, and sometimes we put some ribs in the tube to keep the float in the center. We don't want the float to get stuck on the wall and slide up and down the wall. We want the tube to stay, we want the float to stay in the center of the tube. So we mold some ribs inside the glass tube, keeps the float centered. And then there's a heavier duty way of doing that. We can make the float, if the float needs to be very heavy, like a hand grenade, we can have it ride up and down on a rod, and that'll keep the float in the center of the tube without banging around on the walls when it gets up to the top of the taper where there's extra room to move around. Okay, so most tubes are going to be conical or rib guided, but for some very high flow applications we can do the rod guided floats. If you put a float in a tapered tube and you try to read it, let's read on a spherical float, let's read the center line. On any other float, let's read the highest, widest edge. And if we're going to, if in this example, plus or minus 10%, so we're going to look at the worst case. If we're trying to read the accuracy, and it's plus or minus 10% of full scale, and the full scale here is 0 to 20. 10% of 20 is 2 units. So if the ball's at 10, the actual flow rate coming out could be 8 to 12, and that would still be within 10% of full scale. And if the ball was down here at 4, what could the actual flow rate be? It could be 2 to 6. It could be half of 4 or 1.5 times 4. So rotometers are not very accurate down at the bottom of the taper. They're more accurate up in the top. The closer you get to full scale, the more accurate they are. If the accuracy statement were to be given in percent of rate or percent of reading, which is not very common for rotometers, but is common for Coriolis and mags and some of the other high-tech, more expensive flow meters. If that accuracy was plus or minus 10% of full scale, it would be 2 units up here. But if the ball's at 10, 10% of 10 is 1 unit, so it could be from 9 to 11 and still be in spec, whereas over here it was from 8 to 12 and still be in spec. Okay, so percent of full scale is accurate up here and here and here. It stays accurate through the entire range. Rotometers are not like that. Rotometers get less accurate at the bottom. If the float is just bobbling around down here at the bottom, it's not really indicating much of anything. It has been sized wrong. Make sure you size your rotometers to where you're going to be using it in the upper third of the scale. Okay? Let's look at the next slide and talk about accuracy. If you really have to have accuracy, you probably need to go with a mag meter or Coriolis meter and pay lots more money to get accuracy, say for custody transfer and things like that. But if you simply want repeatability, rotometers are going to be very repeatable. May give you the wrong answer, but it'll give you the wrong answer every single day, which if you set the flow, if you open the valve and set the flow to where the correct amount is going to the process, and the guy running the process is happy with that flow, you can put a mark on here and have all the operators keep the ball at that position, and it will be repeatable. You'll always have that same flow going downstream. So repeatability is a strong suit for rotometers. As well as, if you remember the other things, it's cost effective, no wires on most of them. They're very easy to own and operate and maintain, and low pressure drops. Okay, so if for some reason the pressure upstream or downstream in a gas system is going to be changing, we're going to want to put a flow controller either on the inlet or on the outlet. It'll be a valve and a diaphragm looking thing shown here that is a flow controller. Sort of looks like a regulator if you take it apart, but it's a flow controller. And we're going to put the flow controller on the inlet side if the supply pressure is fluctuating, and we're going to put the flow controller and valve on the outlet of the rotometer if the downstream pressure is fluctuating. And what happens inside here, and we're better off if you get a copy of these slides from my team Brooks under Hatfield Training, What's Up with VA Meters. That's where you can find all these slides. But what you're going to see in here is if you put the flow controller on the inlet, it's going to hold a constant pressure drop across the orifice in the needle valve. So if the supply pressure changes, the spring-opposed diaphragm will hold a constant pressure drop across that orifice, and it will make the ball stay still. So the supply pressure can be changing for any number of reasons, and the ball will stay still. More common to that is we'll put it on the outlet side because the downstream pressure is changing. Say we're putting this gas into a tank, putting it into the bottom of a tank, and the level of that tank changes during the day. It takes more pressure to sparge or to put the air or gas in the bottom of the tank when the tank is full than it does when the tank is empty. So as the level in the tank changes, the back pressure on my system changes. When we put the flow controller here, and this will shield the flow element, the tube and float inside here, it'll shield that from the fluctuating pressure. So these are called an 8800 flow controller and 8900 flow controller when they're mounted on show rates. Okay, so keep that in mind. Look, we're out of slides, so it's time to wind this down. I could ask if there's any questions, but you're not out there in a live audience. I'm talking to my desktop here. If you do have any questions, please contact your regional manager or the customer service guys at Brooks in Hatfield, or feel free to contact me. My name again is Nigel, Nigel .Glover, Glover, at brooksinstrument.com. And I sure enjoyed talking to you about flow meters today, and good luck out there selling Brooks. Thank you. Let's see if I can turn this off. There we go.